Hi, my name is Cameron Calvati. For my Visual Python project, I created a simulation of a golf swing that demonstrates conservation laws and projectile motion. So the simulation assumes a circular club path, which is not reflective of a real golf swing, and it treats the collision as between the ball and the club as an elastic collision. So I start off by creating a fairway, a ball, and a club. So the fairway is a box of length 200, height 0.2, and width of 50. So I'm just establishing it in meters. I'm making sure all dimensions are proportional to one another. The ball is a sphere. I give it a position and a radius. The radius is reflective of an actual golf ball's radius, just magnified by 50x. I give the ball a mass, the real mass of a golf ball, in kilograms. And then I create the club, which is a thin cylinder. I make its position, I establish that relative to the position of the ball because I want it to be left of the ball at the start. So I take into account the size of the club and the radius of the sphere. Here I give the club a mass, and I define two quantities here: ball speed multiple, and launch angle, which I will come back to later. Here I establish the gravitational constant g, uh, time, delta time, which is how much time passes by each run of a loop, and then here's the angle of the golf club at the start of the swing, and potential energy and kinetic energy trackers. So the start of the swing, or the backswing, is the first loop. So while t is less than or equal to 1, I set the rate equal to 100 to keep it in real time. And so the swinging of the club is just rotation. So I have the club rotate. To rotate an object, you have to rotate it about an axis and an origin. So I rotate it about the z-axis, so it is a circular rotation relative to the viewer. And the origin, I just made it mirror the position of the club, but I also take into account the average arm length of a person, but magnified by 5x. So I get a more realistic rotation. Above, I'm just keeping track of the angle as it updates. So at the top of the swing, at the beginning of the swing, rather, the club starts at an angle of 3 pi over 2, and I want it to end at pi over 2. So after 1 second, or 100 times dt, it should change by an angle of pi. So that's the angle part of the rotation right there. So I'm also keeping track of potential energy. So potential energy is mgh in this case. So the mass of the club times g times the position of y. But position of y calculates the position of the center of the club, and so it doesn't take into account the full size of the club. And since the club head's at the bottom, you need to take into account the full size. So just some simple trig using a triangle to calculate the portion of the club above the center. And here I update time. So by the end of this loop, it should be at the top of the swing. So here I define PE max. I set it equal to PE at the top of the backswing. That's the max potential energy, and I print that out. So next we have the downswing, which is another loop. So I say while time is less than or equal to 2, just one more second. Once again, in real time. It's essentially the same code as before, but I'm increasing the angle, so it is a downswing. And then I am updating time once again and calculating potential energy. I'm also calculating kinetic energy, which is just the difference in max potential energy and current potential energy. At the end, I print out kinetic energy, and then I begin some calculations. So the club head speed is calculated through the formula kinetic energy is equal to 1/2 mass times velocity squared. So to solve for v, you have to find the square root of 2 times the kinetic energy divided by the mass of the club. And then I print that out. and then I define the momentum of the club, which is just mass times velocity. And so I'm assuming that the collision between the ball and the ball and the club is an elastic collision, as I mentioned earlier. So momentum and kinetic energy is conserved. So to find the ball speed, you have a system of equations reflecting momentum and kinetic energy conservation. And so you solve for ball speed, and you are left with a quadratic equation in standard form. And so to calculate this independent of specific values, I look at that quadratic function in standard form, which is ax squared plus bx plus c, and I define a, b, and c, which is all proportional to established constants, constants that we defined earlier in the simulation. And so when you have find a, b, and c, you can use the quadratic formula. So at the bottom here, I define my own function, call it QR for quadratic, and it just simulates the quadratic formula. So I have the discriminant, b squared minus 4ac, and then there are two possible solutions, and I return the positive one. So going back to the code, so yeah, as I mentioned before, I found a, b, and c, and then I plug it into the quadratic formula function I find below. And so the ball speed multiple, I defined that earlier, so I set it to 4.5 right here. And as I mentioned before, since this simulation does not take into account force generated by the golfer, because it's just a circular rotation and energy conservation, it does not create a realistic ball speed to create a realistic golf swing. So I have to multiply it by a ball speed multiple, so you get a flight of a golf ball, which is comparable to an actual flight. And so next I define the momentum of the ball, which is mass times the components of velocity, because you have to get the components of velocity for projectile motion. And I just reset time to 0. And so the follow through in the projectile motion of the ball is one final loop. So I say while the position of the ball is less than the starting, or the y position rather, is less than the starting y position, once again in real time. And so the follow through is just more angular rotation until it is back at the top of the backswing, but same position, but this time as a follow through, which is going to get you to pi over 2, and 5 pi over 2 is the same thing, just 2 pi or more. So the same rotation as before. And so I calculate the net force, which is just the force of gravity, which is mg. And so I'm updating the momentum of the ball, which is the momentum plus an impulse, so the net force times time. And then I'm updating the position of the ball, which is the position plus velocity times time, because momentum divided by mass is equal to velocity. And then I'm updating time. So once that loop concludes, I calculate the distance the ball traveled, which is just the position at the end of the flight plus 90, to take into account the fact that the initial position was x is equal to negative 90. And you know that the time of max height is when the y velocity is equal to 0. So you can calculate the max height time using projectile motion equations. And then you plug that in to find the max height. So here I print the flight time, the distance the ball traveled in its max height, and the ball speed. And that is the conclusion of the code. So I'm going to run the program, run the simulation. I'm just going to be kind of a generic ball flight at first. Backswing, downswing, follow through, and projectile motion. So the ball traveled 195 meters and its max height was 26 meters. So kind of reflective of a high launch driver swing for like a typical amateur player. And so you can change the mass of the club and the launch angle, um, which I forgot to mention earlier, but the launch angle is important because that is how you find the components of ball speed, which is important for projectile motion. Anyway, so you can change these variables to alter ball flight. So let's say I want to increase the mass of the club, but decrease the launch angle. I'm going to get a different ball flight. So lower ball flight, since I increase the mass of the club, the distance actually increased 215 meters, but max height was lower. So anyways, so yeah, that is my Visual Python simulation. Hope this is helpful.